we have a point source or an object, and a rays of light is going out from the object, and you have a lens which is going to collect all the rays and bring them to a focus at a point, basically create the image of the object. So we have different phenomenon going on, one after the other. First, light rays go out from the object and travel the distance from the object to the first surface of the lens. So this we call free space propagation in air. Self-explanatory term. Then we have refraction at air-glass interface. So the light rays will interact with this interface and start bending in, as shown in this animation. So suppose up till here is your free space propagation, and this is where refraction is taking place. So this is refraction at air-glass interface. Then light is going to propagate inside the glass, inside the thickness of the lens. Oops. Oh, here is the chat. Okay, I just found the chats. Okay, I can also keep an eye on the chat. Yeah. So then you can see the light is propagating inside the lens. So here, so that is free space propagation inside the glass. And finally, if you have another curved surface, just for the simplicity of the animation, I didn't curve the second surface. I just kept it straight, but basically you would have another refraction at the second curved surface, and then light will propagate in free space in air again. So we have to analyze these 1, 2, 3, 4, 5 situations. But essentially, there's actually two things going on. One is free space propagation and one is refraction. The free space propagation might be in air or inside glass, but it's the same phenomenon. Only the refractive index will change. In air, it will be 1. In glass, it will be 1.5. And refraction at two interfaces is going on. So essentially, there are two phenomena that we have to study. And if we understand those, we should be able to analyze these systems. So going forward, one important thing to keep in mind is an approximation which is used in geometric optics. It's called the Paraxial Approximation. And Paraxial Approximation states that all these angles subtended by the rays in geometric optics are pretty small, which means that the rays are close to the optical axis. Right, so this angle subtended by the ray, and the optical axis is, by the way, this horizontal axis. This angle epsilon is very small, which means that you can use your trigonometric approximations such as sine of that angle is that angle, tangent of that angle is that angle, and cosine is equal to 1. So all the problems that we are going to solve in this class are valid for angles which are smaller than 30 degrees. Which is okay for the time to assume. So next, in paraxial approximation, what happens is if we assume these angles are very small, it means that the distance between the ray which is hitting the curved surface at this point and the ray which is hitting the curved surface at this point is also very small. So it is okay to assume to neglect this small distance basically. So now I'll resort to my PowerPoint again. So in the PowerPoint, we see that this is the paraxial approximation ray. So I've drawn this huge curved surface, which means that if the angle subtended is very small, this region, you can basically look at it in the form of a straight line. So this small distance can be ignored, like between where the ray hits here and here. So next, we have to keep in mind a small trigonometric identity, which is going to be very helpful in solving this math, is the relationship between the arc length and the radius. So if you have this section of arc, which is of length S, and I've drawn a radius going from the center to this point as R, and the radius subtends an angle theta with the horizontal axis, your arc length S equals R times theta. So this we also know from high school, just something that we should keep in mind. Now the interesting thing is, because I said we can ignore the small distance of the small gap because the angle is very small, the vertical height H and the curved arc S, they almost have the same lengths. So from S equals R theta in the paraxial approximation, we can say H equals S. So H equals R theta. Okay. Now, going forward into analyzing how the lens works, we are going to zoom in to this small region for the next slide. So in the next slide, when I draw this is basically a zoomed in version of this region. Okay, so I have approximated the arc into this straight line because I've zoomed in here, and I have drawn my ray of light going in and so on. So now we will analyze how the light ray, what happens to it like in free space. What are the equations that govern the behavior of light traveling in free space? Okay, so yeah, so this is basically what these next slides are going to talk about. Usually this is the math that I work out, so I'll just resort to this PowerPoint for this presentation. So I have defined the ray of light using this arrow, and the ray of light is a very general ray, which means that it has a height x0 or x0 from the optical axis. And from this point, the light ray is going out at an angle alpha 0 subtended with the optical axis. So this blue line is the optical axis, and this dotted line is parallel to this. So same angle is subtended, alpha 0. So after suppose traversing a distance of d01 in air, the ray of light arrived at this point. So now its height has changed. We can see x0 has now become x1, like it has gained some height from the optical axis. However, we can see that the light ray did not change its angle because it did not interact with any different medium up till this point. So the second medium is on the right side of the vertical line, which is glass. Okay. So the second phenomenon is going to be refraction at the spherical surface, where the light ray is going to change the angle when going into the glass. It will change the angle, but its height will remain the same, because the refraction phenomenon takes place just at this point, which is on the interface between the two media. And the third phenomenon is that the light ray is going to propagate further inside the glass. So this will be similar to propagation in air, which means the angle will not change, but it will gain some height from the optical axis. So for free space propagation, angle doesn't change. It just changes the distance away from the optical axis. For refraction, the distance from optical axis remains the same, but the angle is changed. Okay. So let's analyze each of these cases one by one. So I have my outputs, which is x2 and alpha 2. So yeah, and I have my input, which is x0 and alpha 0. So I have to figure out what is the relationship between these two. I've drawn the radius from the center of the spherical surface to this point, and the length of the radius is r. Now first we will look into the free space propagation in air case. Let's analyze that case first. And for that, let's concentrate on this triangle that I have drawn over here. Okay, in orange. So in this triangle, we have our tan alpha 0, tan of this angle, equals this small height h over d01, which is shown over here. Now we have to remember our paraxial approximation, which means tan of the angle becomes the angle itself. So it becomes alpha 0 or alpha 0 equals h, the small height, over d01. Or we can write h equals alpha 0 times d01. So this is one of our equations. Okay. So again, the goal is to find a relationship between the output side and the input side. Okay. So what is the height x1? X1 is basically x0 plus h. So x0 plus h equals x0 plus h, which was alpha 0 times d01 that we derived here. So this is x1 equals x0 plus alpha 0 d01. Okay. So just looking at free space propagation in air case separately, this is the relationship between the small output here, which is x1, and the input, which is x naught. So I have put that equation over here. This is the place where I'll save all the equations that I derived. So your x1, your x1 equals x naught plus alpha naught times d01. Now the second thing to equate are the angles. The angle is unchanged, like we saw, because it's just propagated and nothing else has happened. So alpha 1 equals alpha 0, same angle. So I will save that over here as well as the second equation. That's done for free space propagation in air. Pretty simple. Second is the refraction at spherical surface. So now the ray has hit this spherical surface. Remember the animation from the lens, and it's going to change its angle. But its height is going to remain the same because it's the same point. Just the direction of the ray is going to bend toward the normal, bend inward, basically. So from the slide which was here for refraction, to analyze refraction, we need the incident light, the normal, and the reflected light, right? So I have drawn those over here. Suppose this is the radius and this is your curved surface, right? So the curved surface this is basically your tangent. So remember, I zoomed into the spherical surface and approximated it as a straight line, right? Vertical straight line. So this is your tangent, which means the radius would be normal to this surface. So I've extended the radius to show the normal to this point. This is your incident ray and this is your refracted ray, right? So basically it's this same slide just turned clockwise 90 degrees is this. Okay, so now let's see what happens. We have to define the angles. The incident angle, which means the angle subtended by the incident ray with the normal, I've defined that as theta 1 over here. And the angle subtended by the refracted ray with the normal, which I've termed as theta 2 over here. Okay. So we will use Snell's law for refraction at the interface of two media. Snell's law is n1 times sine theta 1 equals n2 times sine theta 2. So n1 basically here, this is air and glass, but in a general case, you can think of as the left side medium has refractive index n1 and right side medium has refractive index n2. Later on, you can substitute n1 for 1 and n2 for 1.5. But let's keep things general over here. So n1 times sine theta 1 equals n2 times sine theta 2. Now we remember our paraxial approximation. So sine theta 1 becomes theta 1, sine theta 2 becomes theta 2. So the equation becomes n1 theta 1 equals n2 theta 2. Second, we relate the heights. Heights are the same because it's at the same point. So x1 prime equals x1. Okay. So we save the height here, equation here, because nothing else to do. x1 equals x1 prime. However, we need to work a little bit more with the angle equation because these theta 1 and theta 2 are angles which I just added to the problem. They are not related till now with the angles that are given to us, like alpha naught, alpha 1, etc. So we have to relate the theta angles with the alpha angles, right? So how do we do that? So what I do over here is, so remember, if you look at this region where I'm pointing with the cursor, I have drawn the angle A. So theta 2 equals A plus alpha 1 prime. So I have to figure out how to relate alpha 1 prime with theta 1, right? So alpha 1 prime equals theta 2 minus A. Okay. Next, we use the arc length relationship. So now we have to figure out what A is because I just added another angle to the picture, A. So what is A? Can I relate it in some way to the terms that I know? Yes, I can. How? Remember the arc length relationship that I first discussed. So S equals R theta. So in this case, this height H or S or x1 prime in our case equals the radius length R times the angle A. Again, because these alternate angles are equal, so this line is parallel to the optical axis. So this angle A is also equal to this angle A. So x1 prime equals R times the angle A. So we are working toward a relationship here. So use arc length relationship to get x1 prime equals R times A. So A now we can figure out is equal to x1 prime divided by R. And finally, we go back to this equation and replace A, and we get x1 prime over R. So alpha 1 prime equals theta 2 minus x1 prime over R. Okay, so we save that equation over here and then work and go forward. So now we have the Snell's law equation, which was here, n1 theta 1 equals n2 theta 2, and an alpha 1 prime equation over here. So these are summarized in here, and we combine these two equations, basically replace theta 2 from the above equation. So theta 2 equals n1 over n2 times theta 1. So I replace that, n1 over n2 times theta 1 minus the second term x1 prime over R. We are almost there. So we just need to replace theta 1 with some angles which are alpha, and we should be good to go. So how do we do that? So now look in this place where I'm pointing with the cursor. And basically I've saved the arc length equation over here where I'm saving my equations for later use. So over here, I extend this parallel line to the optical axis toward the left. And I define another new angle, B, over here. Oops, B over here. So alpha naught was defined over here. Again, alternate angle rule. This angle is also alpha naught. So we have alpha naught, B, and we have theta 1. So what is theta 1? Theta 1 is B plus alpha naught. So we are almost getting there. Now concentrate on these two regions, right? So we are going to use the opposite angle. So this line, which is the radius, and the optical axis, they intersect each other. So these opposite angles, which is B and A, are also equal to each other. So B equals A. So in this equation, alpha 1 prime, I rewrite it over here, replace theta 1 by B plus alpha naught, like so. Everything else remains the same. And then replace B by A. So everything else is here, remaining the same, just B got replaced by A. And from above, where I was saving equations, I have alpha 1 equals alpha naught. So I replace alpha naught by alpha 1. So summarizing, I've just same equation which is here, I've written over here. Alpha 1 prime has now been related to alpha 1, which was the angle at which the ray was coming in, and the alpha 1 prime was the angle at which the ray was going out, right? Oh, sorry. So also I replaced A with x1 prime over R, the arc length relationship. So all the extra angles that I introduced, like theta 1, theta 2, A, and B, have now been completely substituted by terms which we know, like x1 prime, n1, n2, alpha 1, and radius of curvature. So alpha 1 prime, the exit angle equals n1 over n2 times this term, which has x1 prime and R from the arc length relationship, alpha 1, because alpha 1 equals alpha naught. And again, the second term from the arc length relationship, from this relationship. Okay. So finally, we have a good form. So I just rearranged the terms like to make them look like a proper equation over here. So I can relate my alpha 1 prime with alpha 1 using n1, n2, and R. So just simplification, nothing else. And you can just work this out by yourself. It will be helpful for you. So, and the slides will be provided. So you just redo the math by hand, I would suggest. Okay, so this is the refraction at spherical surface equation. Free space propagation equations were here, the height and the angle, refraction height and angle, done. So I save this over here. So I ran out of space. So I basically moved everything down here. Okay, so next we have to do free space propagation in glass. It will be exactly the same as the previous time, just to replace the values with the new values. So you had x1 equals x0 plus alpha naught times d01. You have x2, in this case this height, oops, in this case this height, x2 equals x1 prime, this height, plus this extra height, which is equal to alpha 1 prime times d12, the distance propagated along the optical axis. And angle doesn't change, so alpha 2, the exit angle, would be equal to alpha 1 prime. I should actually draw the alpha 2, which is basically extending this and drawing another angle. I'll do that before I share the slides. So that's your final angle, right? So to summarize, the three phenomenon that took place: free space propagation in air, refraction at spherical surface, free space propagation in glass, all the geometry that we worked out over here, and all the three set of equations that we made, right here. So these are for general media, like I said. For specific media like air and glass, just replace the values of N1 and N2 and so on. So we have all these sets of equations. The final thing which remains is to equate x2 with x1, x2 with x0 and alpha 2 with alpha naught. So I didn't work that out here, but it's pretty straightforward. Just start with this equation, start with the third equation, replace x1 prime from the second equation, replace alpha 1 prime from the second equation, replace alpha 1 from the first equation. So all the terms will just get substituted, and you will have your final equation. You'll have your final equation equating x2, the final height, with x0, the first height, and all other terms which are known to us. And alpha 2, again, I'll draw this alpha 2, which is basically just extending this here, alpha 2 with alpha naught and x0. So these two equations are very important for us to remember in analyzing these optical systems. So we have basically covered up till here, where these equations are given. So the math wasn't worked out here, so I've added these slides to work out the math, and you can redo it by yourself later on. So again, three sets of equations are also provided over here. Propagation through distance 0, 1 is what I termed as free space propagation in air. Refraction at spherical surface. So again, first set, second set, and again, second propagation, so third set. Over here, I also pointed out my first set, second set, third set, and putting them together is this equation. Putting them together is this equation. Notice there is a typo in the PDF, so this R should not be there. So I will correct that before I post it. So this R is not there, basically. That's a mistake in the PDF. Okay, any questions about the math? No. Yeah, just work it out once by yourself. And if you have any questions, post on Slack. Since I managed to finally get on there last night, I'll respond to them. I think it's pretty straightforward. You just have to remember your geometry, trigonometry, all these identities, relationships, and so on. And that's it. Okay, so next slide talks about some sign conventions that are used when solving these problems. Just some things to keep in mind for when you are asked to solve problems. For like, this slide is very important for the midterm, right? So if in the midterm you're asked to solve some problems, and if you mess up the sign conventions, ultimately your answer is not going to be correct. So always refer to this slide.
So will those information be included in the exam, or?
Sorry, which one?
The former information, the reflection, all those things, will they be included in the exam?
Yeah, I think up to September or whatever date, I think October, some date Dr. Menon mentioned that is in the midterm. So all these math is in the midterm. But we'll see that you won't have to work out the geometry, because we'll learn something else in the second part of the geometric optics lecture called the matrix formulations. Actually, you have to stress more on that. So this is like the background math that I discussed. You will not be asked to derive this, let's say. But
Yeah, so
there are more interesting problems that we will work out. Yeah.
yeah, that's a good way to say it, Pratham. You're absolutely right. Let me make 2 important points about the midterm. First of all, you don't have to memorize anything. All the exams that I have in this class are open book, open internet. And of course, it's an honor code that you don't communicate with anybody. Again, the goal is for you to learn. The most important thing is to gain intuition. So the math is important for you to work out. So definitely you need to work out, but you need to understand what it is that you're working out. Okay. And the exam will really focus on that part of it. The other thing I want to make it very clear is that even if your final answer is incorrect, you will still get points if your approach is correct. So this is, again, in my mind, the approach is much more important. How you approach the problem, how you try to solve the problem is much more important than that final answer.
Thanks for the information. And sorry, I forgot about it. Last time you mentioned, I think you said final was optional for like one of the session. Which session was that?
Section 90, the online students.
090.
Oh, okay, cool. Yes, thanks.
And also I should, as I mentioned at the beginning, everything up to the midterm review, which I believe is October 13th, is included will be included in the midterm.
Okay, cool. Thanks.
Yeah, so like Dr. Menon mentioned that if you will have access to the slides. So, and I will also do the midterm review. I'm doing the midterm review as well. So I'll go over these again once. So sign convention slide is very important. So when you solve your geometric optics problem, and there will be one, don't forget this slide, basically. So what it says is light travels from left to right is convention. And if light travels from left to right, the radius of curvature is positive when surface is convex, like bend like this, convex toward the left. Longitudinal distances are positive if pointing to the right, and lateral distances are positive when pointing up, and the ray angles are positive pointing in the counterclockwise direction. Just keep these values in mind. So when you plug in the radius of curvature, if the surface is concave, like it's bent the other way, make sure you put a negative sign in front and so on. Okay, so now this is a special case for on-axis image formation. So what we discussed till here was the very general situation, right? Everything is included, like general ray, general propagation in free space, general lens, general image formation. So now we look at a special case of on-axis image formation. So what you have is a point on the optical axis from which a ray is going out. It is suffering refraction at the interface between the two media, and it is bending inward to form an image P of the point object S on the optical axis. So how are you going to solve this equation? Like what relationships can we derive from this? So we'll just, this is how you put the equations into use basically. So we'll just resort to these general equations and analyze the special case and plug in some values. So one thing we can directly see in the general equation, the ray had a height above the optical axis. In the special case, there is no height, so x0 equals 0. And all rays, irrespective of which angles they are going out, have to be collected to the point P, irrespective of the angle, to form an image, right? Which means that this second term can be set to 0. There shouldn't be any angle dependence for the image to form. So if we set all this term to 0 and solve the equation, we basically get this. So I've done that over here as well. You can follow the math. So just I've reproduced the drawing over here, written my equations. I've written that here x0 equals x2 equals 0, and all rays must reach P, which means this second term in the first equation can be set to 0. Then I've done some simple math like multiplied by n1, n2, and d1, d01, d02, and so on, and basically simplified the equation to get this. So n2, or in this case n prime, over d12 plus n1, in this case n, over d01 equals n2 minus n1, that is n prime minus n, over r, which is the radius of curvature of the spherical surface. So same over here, and same equation that I derived. Why this equation is important is because this is also the imaging equation, as we will see later on. And this right-hand side defines the power of the spherical surface. The units of the power is diopters, or inverse of length, so 1 over meter. Next is another special case where you have light rays coming from infinity, parallel rays coming from infinity, like suppose light rays from the sun coming toward the earth can be assumed to be parallel rays because the distance is so large. So image of point object at infinity. So very far away you have an object, all rays are coming in parallel. What happens to your equations? Again, you can work these out by yourself. I have also worked out the math. Just do it, tally with the whatever I solved and double check. And so I have my set of equations. Here I write x2 again becomes 0 because all the rays come to a focus at a point. And alpha naught equals alpha 1 equals 0, right? Because all the lines are parallel to the optical axis. So no angle is subtended by the incident rays. So those angles are 0. So I plug those into these equations and I solve for d12, which is this distance, is given by minus n prime over r, or n2 r, not over r, minus n2 r or n prime r over n1 minus n2. So this d12 is also defined as the focal length of the lens. How do we define the focal length of the lens? If we have parallel rays coming in, all the parallel rays will always be focused at the focal plane of the lens, or the focal length away from this interface. This is also what was shown in the animation, by the way. So in the animation, these rays are parallel rays. We might look, if you look carefully, all these are straight lines. So these are parallel rays coming in, and that's exactly how I drew the arrows. The arrows are horizontally parallel to each other. And you see what happens is the arrows show the bending, and you can see how the waves are also bent, and they come to a focus. So see, it's getting smaller in size, and roughly here is where the focus is. So this is the focus of the lens. So all the parallel rays are focused at this point. And the light energy is also being concentrated because the energy which was spread out over this large area is being concentrated to this small area as well. So this is the wave optics animation of this problem, that this special case problem, parallel rays going in this problem. The animation is exactly what is shown over here. Okay, so this is point object imaged at infinity, just the reverse. I think I'll leave this up. You can take a look at what this is, what this case is, and solve the problem by yourself. And if you have questions, ask me later on. Okay, so I think I have about 10 minutes. I'm not sure if I want to start the matrix formulation right now. The class ends at 1:45, right? So yeah, maybe I think I can.
Yeah, I think we should stop because that's a lot of material, and I don't want to overwhelm.
Yeah, because that's also a new thing. So let's do this in the next class. Just
on Thursday.
Go over the math for the time being that we discussed. Yeah.
So as Apratim mentioned, it's important you can go back and watch the video and certainly do that, but certainly try to work out the math yourself of the basic concepts. This is quite important. In the exam, of course, we won't ask you to derive any of the stuff, but for the purposes of understanding, I would like you to do it yourself by hand. And again, if you go work at Facebook or Google or Amazon, you will never do this by hand. You will use fairly sophisticated software to do this, as you will learn during this class. But it is very, treating a piece of software as a black box is an extremely bad idea. You need to really have a feeling for what it is doing. Because if it gives you unphysical solutions, which it can many times, you need to be able to know it. And this is an important skill. So in the interest of not overwhelming you, I'd like to stop the class a little early today, but let's see if there are any questions first. Okay, and that's fine. You will have questions, by the way, and it's okay to have questions because these things are not necessarily simple. So just post them on Slack, and again, just email me or Apratim. Okay, so we will stop here. Again, let me remind you to contact your teammates, and all the notes will be posted today. Give us a few hours. Typically, everything will be posted the lecture before the lecture. Worst case, it'll be the same day as the lecture. Okay, I don't have anything else. So let's adjourn now, and yeah, good luck, and hopefully you can gain some intuition from the concepts that were discussed today. Great, thank you, Apratim. Thank you, everyone. Take care. We'll see you all on Thursday.
Thank you.